There we
Think
go.
of your network like a legendary rock band. Every server, endpoint, and data flow is a band member playing their part, tight, in sync, and bringing the house down. But when one guitar goes out of tune or the drummer skips a beat, even the smallest misstep can potentially throw off the whole show. And that's where behavioral anomaly detection comes in. It's your backstage sound engineer with a sixth sense for when something's off. It listens to the rhythm of your network, learns what normal sounds like, and instantly calls out the weird solos before they turn into a full blown meltdown. And so today we're diving into how this engine spots the off notes, flags the strange riffs, and helps keep your network running like a sold out arena tour. I'm Peter from the marketing team. Let's plug in, turn it up, and turn it over to Plixer data scientist Adam Howarth. How's it going, Adam?
Good, Peter. Thank you for the intro. I always enjoy the fun music analogies.
Right
Um,
on.
yeah, so thank you everyone for joining us today. We're going to take a deeper dive into the behavioral clustering anomaly detection system in our AI engine product. A lot of the machine learning analytics that run can kind of feel like a black box sometimes. So I think it's beneficial just to run through kind of some of the lower level mechanics of what's actually going on and how it provides kind of value to your flow analytics pipeline.
And
So
real quick, we
yeah,
sorry to interrupt, Adam. We do have our QA turned on for episode 2 of the Tech Talk. So if something pops while we're presenting, you can certainly drop it in the QA at the bottom of your screen or to the left or right, depending on how you have the viewing configured.
yeah, for sure. We can circle back to those at the end, and then anything that's a little more involved, I can follow up with you on offline. But to begin, I just want to start at a high level of kind of what, just for context, what is the AI engine? So the Plixer One platform, it serves a lot of roles, right? Its primary function is to collect and analyze all of the flow data from all sorts of different devices in your environment. And at the end of the day, it can store that data for however long is required for your retention policies. So that ultimately makes kind of the core unit of the Plixer One platform responsible for keeping that data and storing it, whereas the AI engine rides as a sidecar to handle the heavy compute, basically kind of separating the burden of what each resource set is responsible for doing. So the AI engine really started when there was a demand for getting Kafka streaming data off of the Flow platform. Kafka is really nice. It's just a general kind of streaming and consumption based platform for getting data into data lakes and other analytic pipelines, things like that. Flow data comes in information elements that are very specific to the IPFix and NetFlow protocol. Our platform has probably the widest library of those definitions, so we're able to decode those things and make the data available in plain text that's actually useful for other analytic pipelines. So ultimately, the first and primary role of the AI engine is it is a Kafka broker for your flow data. So if you're using the AI engine, not only do you have all the analytics and specifically the behavioral stuff we'll talk about today, but you can also tap into that Kafka stream and get a copy of the data for any kind of exogenous use that you have for it. As soon as you set up AI engine, you have that Kafka broker receiving data and ready to be subscribed to out of the box. Which is kind of a process that otherwise is somewhat burdensome. So that's immediately an exciting thing from a data science point of view. If you have any kind of ideas or exploratory research you want to do with your flow data, this endpoint makes that available to you in really any environment that you want to run your compute in. So that's just kind of one main point, and ultimately a lot of these algorithms came from, well, now that we have a Kafka stream, what are the things that we would really like to do if we had the ability to kind of move the heavy compute away from kind of the core of the platform and handle it off to the side. So we have a whole suite of non-deterministic analytics. By non-deterministic analytics, I mean the core platform has a ton of tests and algorithms that are run against all of your flow data for things that are common across all environments. So things like port scans, things like long running flows and persistent flow risks. Those are things that we can just run kind of a static test against and tell you yes or no if that's occurring in your environment. The algorithms that run on the AI engine are things that maybe need to learn about specific usage patterns in your network itself. I've spoken with other data scientists that work in the space, and network transferability is just one thing that doesn't really exist in the sense that every network serves a separate role and the way that it's used is going to be different. So, in order to baseline and learn what's normal or abnormal for a network, some of the algorithms actually do need to learn from the data that it's seeing. And that's really the primary role of all of these functions. So finally, running real-time inference, it turns out, and we'll talk about flow volume in a second, but it turns out when you're getting hundreds and hundreds of thousands of events a second in many cases, actually evaluating each of those against whatever sort of tests your models can provide is actually kind of a difficult challenge also. So that is really the primary role of the AI engine. And the reason it's kind of a separate unit is because it's a really high compute and intense situation to not only build these models and train these models across all of the different algorithms, but also to run inference against the live observations that are coming into the platform. So this includes the forecasting engine for making predictions into the future based on flow data we've collected, capacity planning, et cetera. Malware traffic classification, where we've basically detonated malware in a lab and collected information about how the network signatures appear around that, and then put some static classifier trees in for looking to see if those patterns exist in your data. Encrypted traffic analysis uses our FlowPro product to get information about TLS connections in your environment, and then profiles those things, looks for weird JA3 signatures, matches those against what we'll talk about in a second, the strange behavioral patterns that are observed. There's an intelligent DNS proxy for reviewing all DNS requests and kind of getting a state of those things. And today we'll talk about the behavior anomaly detection. And then last Tech Talk, we talked about the graph-based anomaly detection engine. Kind of what is the problem at a high level? So we have tens of thousands in many cases of hosts communicating on a network. And the way that they use the network is going to be mappable into different behavioral clusters. So the way that we think about this is temporally, so across time. Last time we had talked about the graph frames and the graph analytics system that looks at instance in time and kind of the network properties of any instance in time. And towards the end of that talk, we had talked about some of the kind of weak spots in that model. And that's covered by this algorithm that actually does look at behaviors over time periods. So those two kind of work in conjunction to isolate incidents. Behavior, how a host is using the network specifically. And then finally, clustering, taking the way that the host uses the network and kind of binning it into known patterns for usage.
So before you move on real quick, there's a question that came up, and I think it's in relation to the last slide. So that's why I interrupted. Is there any machine learning to analyze the trends and predict a performance?
Yeah, so in Scrutinizer, the kind of workflow that we are used to is isolating kind of a situation that we're interested in and pulling the data forward in a reporting type of view. That first function that was on the list in the previous slide, the forecasting engine that runs on the AI component, is able to take any report from Scrutinizer and project it into the future. So one thing that's nice about this is tools like that typically exist for SNMP type data, but in that case, you're only going to see aggregate interface usage. Applying that to flow data, we can actually see on a per application, per host, per QoS queue, really anything that can be reported in flow data. We can break the data, the actual individual data sets down by whatever class they belong to, and then project those into the future. So around performance, typically what I do is look at the forecasting capacity around latency metrics and jitter metrics. So any application on the network, there's a lot of exporting. Our FlowPro product does it, but there's also Cisco AVC, Silver Peak, quite a few devices that can export TCP latency and UDP based jitter statistics, as well as packet loss, retransmits, things like that. The forecasting engine works really well against that kind of data because it's what we refer to as stationary, in the sense that is going to oscillate around kind of a known value. In the case of jitter, you could think about the jitter buffer that you'd tune on an RTP application, basically how long of a window is open in order to absorb packets. So that way any inter-packet arrival time, which is what jitter is, can be absorbed in that buffer. And then by the time the media is replayed, all the frames are in sequence and, the video, my hands wave and it stays smooth over kind of whatever media platform is displaying it. So the forecasting engine really does a great job around any performance metrics. Obviously, if you're looking at an application or an application that's maybe moving to the cloud, it does a good job of identifying trends and projecting those trends into the future for capacity planning usage. But in the case of performance, we would really be looking at, again, like application delay, network delay, either on the client side or the server side, or jitter in the case of RTP or any, UDP-based streaming media. Additionally, it'll develop as we talk through this. Any behavioral pattern, I think a lot of times we immediately default to thinking security use cases when we talk about this. But as we'll see, these are also applied to aggregate traffic on network interfaces. So we can actually identify behavioral changes in how network interfaces are being used to identify any period of time where maybe usage is spiking and it wasn't expected, or in the availability case, it's actually dropped at a period of time where we didn't expect to see, less usage. Thank you for bringing that forward, Peter.
Yeah.
So the main goal of most of these algorithms, but very specifically the behavioral clustering one, is volume reduction. So at full capacity, a single collector on the platform can ingest 100,000 flows per second or network observations per second. That basically means over the course of a day, you're looking at somewhere in the neighborhood of 8.6 billion individual events. So we start to get to numbers where even the most diligent analyst they're going to get overwhelmed by volume. So the main goal of behavioral anomaly detection is to take that huge set of input and distill it down to a smaller set of events that are interesting. And then further, once we've distilled down to that smaller set of events, we can now pass those through stricter deterministic tests to identify very specific issues that might be happening with those hosts. Again, performance or security. One thing I always say internally a lot is really all, typically in the security case, you think of like the CIA triad: confidentiality, integrity, and availability. All availability problems are also performance problems. So whether it's maliciously happening or the actual usage on your network at any point in time is causing an availability problem, that's going to be degrading the performance of applications on the network. So the first thing that happens in the behavioral clustering pipeline is we take in that Kafka stream of observations. So if we look, we have some internal host on an ephemeral port talking to a public host over 443. So we know that our local host is going to be the client in that conversation, and the server is something out on the internet. So the first thing that happens is all of the observations are sorted into what dimensions are important. We'll talk about the dimensions a little bit later. And then an import transform is applied and an aggregation. So what that allows us to do is for every monitored network interface and every monitored host, we are also looking on a per protocol and port combination as to how that host or, again, network interface typically is going to interface with the network and use other resources. What gets important is that input transformation component. Okay, these are the flow dimensions. So within the product, we have a big list. I think there's slightly over 200 different combinations across client protocol and port, server protocol and port, and then network interface protocol and port. So those are kind of the basis of what we're looking at to identify behaviors. And you can ultimately go in the product and toggle these on and off for whatever's interesting for your environment, or just leave everything on for kind of a total capture of everything. But that's something that's important to remember, is that we're not just building a model for every host that comes in. We're actually building hundreds of models against every individual entity that we're studying. So the first thing is that input transformation. So it begins with a time series aggregation where in each case, across those dimensions, depending on what's important, we're either looking at kind of the packet delta for the flow, the octet delta, how many bytes moved around for the flow, or the density of the bytes per packet over the flow. That metric is then kept over a 32-minute vector that is effectively a time series. So in the graph on the left, you can just think of it as its usage, and then its usage at minute n-1, n-2, all the way back to n-31. And that represents the at that instance in time what the exact behavior is for that host, again, against whatever that aggregation criteria was, packet, octet, whatever. Those kind of waveforms ultimately are moved into a vector space. In this case, there's kind of a reduction. We have another question we'll look at in a second. There's a reduction in these images just so they make sense to us. Ultimately, this is because it's a 32 component vector, it's 32 dimensional space. We can't really see beyond 3D. You can start to kind of use colors and stuff to see fourth and fifth dimensional properties, but kind of an easy way of thinking about it is like a roller coaster. You know, a roller coaster goes all over the place, and you can map in 3D space where that track is at any point, but you'd actually need like a fourth dimensional value to evaluate, you know, is it upside down at this point? What's the orientation? And then further, you start to think like, how would I represent a fifth and a sixth and a seventh dimension? So for human understanding, in a lot of these images, I've baked things down to 2 dimensions, and there's some principal component analysis and TS&E we can look at later to really see an actual example of one of the inputs to the training model and kind of what that would look like if you could crunch it down into a more understandable dimensionality. But this is ultimately the first transform, is grabbing these time series, evaluating the behavior for that instant, considering its lag in the past, and then mapping that into a vector space so we can cluster those points.
And then the image on the left, the colors represent whether it's a server, a client, or an interface. Is that
they're just different
random?
different ones. They could be client, they could be network or server usage.
Got it.
Again, across those dimensions that we talked about in the previous slide.
Yeah.
Some of it's I just used wildly different colors, so it was
To
obviously different.
differentiate
Yeah.
a pretty thing. So the question, Adam, is from Alex again, from the same question, not same question, same individual. So in a VXLAN environment, will the NetFlow Scrutinizer Plixer 1 be helpful to troubleshoot underlay or troubleshoot underlay and overlay both? If yes, can you give a quick example how this can be accomplished? I don't know if I
Yeah.
read it properly, but you
Yeah,
got it up.
this is one I can certainly follow up with offline, just because it kind of goes more into the topology of where to position exporters that are getting data for us. But in many of the SD-WAN solutions, we can both get visibility kind of into the dynamic tunnels effectively that are set up between locations, as well as the external environment around it. So I'll make a note, and we can talk about that offline, and I'll shoot you an email. But that really comes down to observability points and what the exporters are able to give visibility into. So ultimately, after that previous step, we take all of those points that, again, time series, they're vectorized. And then again, this is just kind of a simple 2-dimensional representation, so it just makes sense to look at as we talk about. So those are clustered. Anybody that's done even some basic machine learning or data science work, k-means is probably the tutorial or the first item that will come up. And it turns out it's actually pretty powerful when you don't know what the different behavioral classes necessarily are for a host, right? So if we're looking at client HTTPS, they may be doing several things over that, some internal API connection, some web browsing they're doing, maybe even Teams is not running in RTP mode, so it's encapsulating all of the traffic for your calls in HTTPS. So within that singular dimensional combination, we'll find that there's several clusters of behavior that happen. And again, this is in 2 dimensions, so this would almost be if our time series was only the current instance and the last minute plotted on X and Y in this case. So once those clusters are formed in the k-means model, it's kind of a simple situation of figuring out who your nearest cluster is and where that belongs. And then ultimately you can derive boundaries by figuring out what points are kind of equidistant between them. So this is kind of a crude example just drawn in just to highlight that point. So at that first stage, we can figure out, there's k top behaviors for an individual host on that port and protocol combination. And then once we've established that, we basically have a space that we can push new points and new observations into on inference and have an idea of where they would land cluster-wise. So just for some clarity, I grabbed an example, and I don't know how much clarity it'll be because it's dimensional dimensionality reduction. But I grabbed an example off of a running machine learning engine and took one of the vector sets that's used for training and did basic PCA on it. So that's on the left hand side. PCA preserves, the actual relationship in the data as best it can while reducing the dimensionality. Again, we're trying to just get to 2D so we can look at it and it makes sense. So in that case, the actual relationship to where the points are do have a relation to what the usage look like over time. And you can see there's kind of some trails where it's very dense at one end, and then there's some structure to it, but it ultimately kind of opens up as it moves to the right. On the right-hand side, there's a TS&E projection. If you've ever done any sort of graph-based visualization, TS&E is a lot closer to force direction, where the space that this is being represented in isn't as important, whereas the clusters are drawn together. So vectors with component similarities get pulled together into clusters, and that's where you can actually start to see that in natural data, there are lots of clusters that do appear from regular usage. And then ultimately, data points that don't really have a lot to do with what's normally happening on that host end up mapping much further away to really their own cluster space. So there's a few examples on that right hand side where you could see things that at least visually would appear to be anomalous. But again, we start to talk in volumes of data where a human analyst can't really keep up with this, and this is also one instance in time. So this is, the amount of time it would take to go through and review this, identify a point. Never mind, the TSNE on this alone took like 8 minutes to run. So
Yeah.
you pretty quickly get to a point where the actual analysis of the data takes so much longer than the input rate of the data that you can't really do this in a manual way. So that's really where this whole pipeline of training these models, building that vector space, and then as we'll talk about next, coming up with the inference pattern for how do we quickly check, on a new observation where it would land in that space and what its kind of behavioral relationship would be to the other things that are happening on that host.
It really looks like, have you ever seen that drone where the three sharks are swimming through that big fish pool, the pool of fish, and all the
Right.
smaller fish are just breaking away as the three sharks are just swimming through? Kind of reminds me of that. And obviously, the left definitely looks like a fish.
Yeah, if anybody's interested, like flocking algorithms are very interesting. There's a lot
Yeah.
of work that's gone into flocking algorithms that it literally describes what you're talking about, where the way schools of fish and stuff move. It's pretty
And the
interesting.
birds all together.
Yeah, we do get to the inference part, right? So again, there's really too much data that the kind of analytic delta, the amount of time we have to make a decision, shrinks down to a point where this kind of has to be a machine learning problem. And ultimately, really, the goal of machine learning is how do we take this kind of long chain of mathematical operations that have to happen and flatten them down into just a quick polynomial that can be evaluated against a new input, and a determination can be made as to whether or not that input belongs to a known behavioral class or not. So we take our new input, it'd be like this blue guy down here. It's not really in a cluster. It's kind of halfway-ish between two of them. And what we can actually do at that point is we compute what's called a silhouette coefficient, which is effectively how strong of a member of whatever class you should technically belong to are you. So if we think
Mm.
about, again, kind of those crude boundary lines that would really just be who's your closest cluster centroid, there's two metrics that are calculated: cohesion, which is the average distance to members of your class, and separation, which is the average distance to members of the nearest alien class that's not, this doesn't belong to based on its centroid distance. So the silhouette calculation is literally that. It's the average separation minus the average cohesion. And then it's just normalized over 1 and -1 by dividing out whatever the maximum is of those two. So at the end of that, we get a score between -1 and 1. And it gives us an idea of how likely it is that that point should belong to the class that it maps to in that vector space. So again, on
Hmm.
inference, we take the point, we've have that time series aggregation, it gets mapped into a vector, it gets plotted into that kind of known space that we've been training on already that's building these various centroids out that represent behavior. And then the new observation gets checked against that kernel space that is where all the centroids are. And this silhouette's calculated to determine if that inference point does or does not belong to a known cluster. So that's kind of the quick way that it scores it. In the
And then if
product,
it is, it then just kind of stays or moves into that grouping of clusters. And then when a new observation or inference comes in, it would then kind of, and that new one becomes the blue dot. The first blue dot on that slide has made its way into one of its little groups, right?
correct, right? So if that is something that happens regularly, and this is something you'll see during kind of initial training phases, if that does represent a class that we just haven't seen a lot of data from, that's why we continuously train these models to
Right.
add those things in. So if they remain anomalous, they remain anomalous. But if more data points kind of join that cohort there, it may form a new centroid. So we know there's a kind of a new behavior that we didn't realize was normal initially, but we kind of learned that over time that it turns out there is a fourth or fifth or 10th or 15th
Yeah.
behavioral class to that. And that's actually what you can see in this. So this is the view in the product. So from the host-based views or the network interface-based views, there's a behavior tab. And you can actually see the boundary around those centroids because effectively you can figure out the silhouette coefficient for all of the elements in any cluster. So you have an idea of what the line would be for, if it's a very loosely bound cluster, you may have lots that are lower on that silhouette metric. But ultimately, we can figure out the variance and kind of statistical properties of any of the clusters and how the points land. And that's used to develop a threshold that effectively encircles that cluster. And now we know, where that silhouette score is going to be acceptable for that class or anomalous for that class. And that's what the green line is on the behavior view in the product. And you can actually see what Peter's talking about there. It does adjust itself over time from learning about those new behavioral classes and clusters or events that may happen. You can think about on that client port protocol, combination server port protocol, network interface, same situation. So after all of those things have happened, we've basically passed that first stage of the volume reduction that we've talked about earlier. We've identified the points in time that these different kind of study entities have behaved in a new or interesting way. And then there's a separate set of deterministic analytics where now that we've identified and figured out exactly when the interesting traffic is, we can push in for further surveillance. So this basically is lots of, again, deterministic tests where we're just checking for, do these properties exist for this host in this period of time because it's already been signaled as behaving differently than usual. And then this ultimately gives us, so the first arrow on the left, all behavioral anomalies you get some visibility into from the alarm view at the center of the Plixer One platform. Just so you know, this host did something different than what it's normally been up to from at least the time that we've been studying it. At that point, the data submit into this qualified deterministic check, checked against a bunch of very specific things that we expect to be a problem if in conjunction with a behavioral anomaly. And then those are further qualified and then pushed into the alarm view. So at the first stage, you get some general visibility into when things are acting differently. And then if anything very specific around a kind of known issue is detected at that same period of time, the alerts are further enriched to be a little bit more specific to things that we can actually attribute into like the MITRE framework as an example. And then the product has a feature called Auto Investigate that effectively knows the ontology of the MITRE framework, the flow of how those events would happen, and can sew several events together to kind of tell that story a little bit better for the triage and response portion of that alarm review. So perfect. That is behavioral clustering. That's the kind of that pipeline. Our next webinar is going to be called Beyond Recovery: How Faster Instance Response Reduces Mean Time to Resolution. That'll be on May 22nd. I look forward to seeing everyone for that one. That should be an interesting talk about kind of that next layer, right? Like this is just one analytic component. There's 50 plus deterministic ones that run directly on the Plixer One platform. There's the suite of things that run out here on the AI engine. So this talk will be focusing more on kind of what does that workflow look like when you're actually relying on all of this analytic output to navigate an incident response scenario.
So I actually have a question, Adam. So last time we dug into the graph-based detection. This time we're in the behavioral based. Is there any, like, can they feed off each other, or, you know, give data? Do they share anything? Is it almost like a daisy chain? You hit one, you go through that, you hit the next. Like, is there any, do they work in conjunction with each other at any point?
Yeah, perfect. So that is basically what that we'll be talking about in that next MTC
Ah,
live talk. Yeah, is we didn't even plan that one, but that does get to that layer of, you know, what does it look like to have violations across these different tests, and then ultimately what does that mean for the kind of the tactics and techniques that are involved, and you know what on kind of the kill chain, where are we in
yeah.
that attack pattern. So yeah, that will be the whole next talk, is what does superposition of all the output from these various components working together kind of get us for an investigative response workflow.
Nice.
Yeah.
That was a good prompt right there, I guess.
Yeah, right, that worked out. So,
Yeah.
um, additionally, Cisco Live is coming up. It's the first week of or second week of June here, June 8th to the 12th. We'll be at booth 1940. We look forward to seeing anyone who's there. We'll have some demos around some of the, you know, we talk about AI on this call. It's really machine learning. The demo that we'll be focusing on at Cisco Live is around more of kind of the LLM type interface that AI has been taken over by, and how we can use that to get to data faster and navigate through the product a little bit more smoothly. So that way, when something does come up and you need to get in and get information about that incident, you know, there's really no barrier of you got to click this and this and this between you and the data you need. It's more just natural language prompting the platform and immediate jump into the information that will help you solve a problem. So other than that, thank you very much. And Peter?
That was, yeah, that was good. I also want to encourage you to follow us on socials at Plixer for Twitter X, and at Plixer1 ONE on the YouTubes, and certainly we got a show corporate page, just Plixer on LinkedIn. We'll see you again in a few weeks for May 22nd. So make sure you tune in for that. For my good pal Adam, I'm Peter, and we're with Plixer. Thanks for watching.
Thank you.